the very beginning, we talked about energy band theory, in which we talked about a graph which was representing the relation between energy levels of an electron when interatomic distance between two silicon or any other semiconductor changes. And we came to a graph which looks like this. In this graph, when the atoms are far enough that they do not interact with each other, therefore act as different identities. If we consider silicon atom, then the electrons reside in energy levels 2p and 2s, and we also know that there are two electrons in the s level and there are two more electrons which are present in 2p subshell. So the energy level for the corresponding electrons will be like this. Now, if we decrease the interatomic spacing of our crystal, then an atom will exert an electric force on its neighbors. Because of this coupling between atoms, the atomic wave functions overlap and the crystal becomes an electronic system which must obey Pauli's exclusion principle. Hence, the 2p and 2s energy levels from all the atoms when comes together must spread out in energy, making an array of different energy levels like this. This band of energies which allow a single electron to exist at a single energy level is called as energy band. The separation between the levels is very small, but since n is very large, the total spread between the minimum and maximum energy may be several electron volts. This large number of discrete but closely spaced energy levels is called an energy band. But the thing is, this concept is not restricted only to semiconductors. As we discussed in the last lecture, that in the non-degenerate semiconductors, the dopands are usually placed far apart from each other so that they do not interact with each other. For a normal non-degenerate semiconductor, dopants are usually mixed in the ratio 1 is to 10 to the power 8 atom. It means that for 10 to the power 8 atoms of silicon, there is only one dopant atom. If you want to understand through a diagram, then assume that in the middle we have a dopant atom and around it we have silicon. And these dots are representing electrons. But the other dopant may be located quite far, and it is so far that it does not interact with each other. But let's say the concentration of the dopant is increased to such a high value that the dopant atoms start interacting with each other. After that, not only the silicon but the dopant energy levels also degenerate and begin to follow this particular graph. As they come close, the energy band of the dopant atoms also degenerates into so many closely spaced energy levels. Now we will analyze band gap narrowing effect through conventional energy band diagrams. At least one thing you can tell from the graph that we have taken n-type semiconductor for the purpose of analysis. As you can see that the dopant energy level is nearer to the conduction band, therefore It means that the extrinsic semiconductor which we have taken into consideration is n-type. Now, here we have a non-degenerate semiconductor, and this is the case when doping concentration Nd is very small compared to Nc, where Nc is the effective density of states in conduction band. But assume that if the doping concentration is comparable to effective density of states, then the dopant energy level will degenerate into a band of energy levels like this, and will not be a single discrete energy level which we usually observe in non-degenerate semiconductor. And because of this degeneration of single discrete dopant energy level into multiple energy bands, these semiconductors are called degenerate semiconductors. Similarly, if you assume that Nd is very much greater than Nc, then there will be a case when the energy band created by the dopant energy level will actually meet the bottom of the conduction band. When this will happen, we can also say that we have more energy levels below the conduction band where electron can reside and can be considered as free electron, which will further increase the conductivity of the semiconductor. And in such cases, the effective conduction band energy level will be changed and will come to the bottom of dopant energy level band, which will eventually decrease the band gap energy. And this whole phenomena of band gap reduction when the doping concentration is too high is referred to as band gap narrowing effect. For finding the change in band gap, we have a formula which is equal to 22 multiplied by Nd divided by 10 to the power 18 raised to the power 1 by 2, and this will come in milli electron volt. This particular formula is not a universal formula, as this is valid only for silicon at room temperature. You can do the similar analysis for p-type semiconductor, where the degenerated acceptor energy level into a band will meet not the bottom of the conduction band but the top of the valence band. And for silicon, the formula will remain the same except Nd will be replaced by Na. Also, when we draw conventional energy band diagram for n-type degenerate semiconductor at 0 Kelvin, then the Fermi level may even go in the conduction band so that the extrinsic semiconductor behave more like metal rather than as a semiconductor.